Hi everybody, my name is Xiao Jianping. My presentation today is about an intrusion detection system, which is autoencoder ensembles for network intrusion detection. My presentation will mainly include 6 parts: introduction, related work, background, proposed model, evaluation and results, conclusion, and future work. As we all know, network intrusion detection systems can effectively detect network attacks. However, the existing network intrusion detection systems have the following defects. First of all, most current solutions often fail to accurately detect unknown attacks and have a high false alarm rate. Secondly, the existing intrusion detection technologies require a lot of time overhead and training data, which is difficult to adapt to the real network environment. Therefore, it is necessary to solve the above problems. As shown in this PPT, there have been some studies on network intrusion detection. The related research work in this field is described below. Considering the high dimensional character of network traffic, data consists of many features. Shall ETL applied HMM to network intrusion detection based on abnormal traffic, took the traffic characteristics extracted based on principal component analysis (PCA) as the input value of HMM, and judged the type of traffic based on the probabilities of output. Chap-Ernie ETL used the Gaussian mixture model method to learn the statistical characteristics of each traffic category, and applied interquartile-based adaptive threshold technology to identify outliers. Lee et al. Proposed an autoencoder intrusion detection system based on random forest algorithm, which used shadow autoencoder neural network to reduce the computational complexity, shorten the detection time, and effectively improve the detection accuracy. Yasser Mixquay et al. Proposed online, unsupervised, and efficient network intrusion detection system, which is capstone based on ANN. In this paper, we use autoencoder as an anomaly detection module, which is inspired by capstone. Okay, next it is background autoencoders. The autoencoder is a core part of the proposed model. Figure 1 illustrates the basic architecture of an autoencoder. The second part of the background is the one-class SVM. The one-class SVM is unsupervised. It is a novelty detection method. The goal of a one-class SVM is to fit a hyperplane as a boundary, which can best include all training data and exclude any other data points. One class SVM is considered to be one of the most mature outlier-based machine learning technologies. After one class SVM being trained, a spherical boundary will be formed. Okay, next, we will introduce the proposed model. The overall framework of the model presented in Fig 2 consists of 3 steps. Next, I will describe these 3 steps in detail. Step 1. Data preprocessing. The two benchmark datasets NSLKDD and CSE-CSE-IDS 2018 used in the experiment need to be preprocessed. Step 2. Feature selection. Recursive feature addition algorithm is applied to select the optimal subset of features. Step 3. Anomaly detection. The anomaly detection part is composed of autoencoder and k-means. After feature selection, AP clustering algorithm is used to group feature subsets. Each features group corresponds to an autoencoder. These autoencoders and ensembles compose to the core of the anomaly detection module, and the normal network data is used to train the detection model. After the model is deployed, the autoencoder processes the new incoming traffic and calculates the RMSE. The RMSE value is used to determine whether the network traffic is normal. K-means algorithm clusters the result according to the RMSE value. In the first part of experiments, we use NSLKD to verify the effectiveness of the recursive feature addition algorithm and conduct classification experiments on one class SVM. We use recursive feature addition algorithm on NSLKD for feature selection. After feature selection, the one-class SVM is trained according to the selected features. The table 6 shows the results of one-class SVM test on NSLKD with all features and the optimal subset of features. Next, we compare the training and the detection time of the one-class SVM model. Before and after feature selection, as shown in Table 7. Therefore, according to the detection results of the NSLKD dataset, the recursive feature addition algorithm is effective. And in the second part of experiments, we evaluate the performance of the proposed anomaly detection model on CSE-CSE-IDS 2018. We compare the experimental results on the sparse and dense matrix. Table 8 is the results of the confusing matrix. The results show that the use of sparse matrix and dense matrix for detection can significantly improve the accuracy of efficiency of detection. For most of the sub-datasets such as botnet, DDoS attack, slow HTTP test, FTP browse false, DDoS attack HOSA, SSH browse false, we can get relatively good detection results. We hope our model can achieve a high recall rate. Table 9 shows the performance of our model and KNet in terms of recall rate. On the same dataset, the experimental results show that the overall recall rate of our model is better than KNet. It is noted that the distribution of normal data and abnormal data in some sub-datasets is unbalanced. Overall, it is clear that our model can maintain good recall rate and adapt well to the environment with unbalanced data distribution. We also compare the detection time by our model and KNet on the same dataset, as shown in Table 10. After splitting the original dataset into the sparse matrix and the dense matrix, the amount of data is significantly reduced, so the detection time will be less. From Table 10, we can see that using KNet for detection takes a long time, because it does not divide the dataset and uses all the features for training. However, the recursive feature addition algorithm of our model also consumes a lot of time, which still needs to be improved. Okay, now we come to the last part, conclusion and future work. Our model FAE is a lightweight intrusion detection model based on feature selection and autoencoder. It consists of the following three parts: data processing, feature selection, and anomaly detection. Experimental results show that our model can speed up training and detection time and accurately detect attacks. And in the future research, we attempt to use real network traffic data to further evaluate our model. And these are references. And that's all. Okay. That's all my presentation. If you have any questions, please feel free to contact me. Thank you.